4-transistor SRAM provide disadvantages in density at the cost of manufacturing complexity. The resistors must have small dimensions and larger values. Generally, the fewer transistors needed per cell, the smaller each cell can be. Since the cost of processing a silicon wafer are relatively fixed, using smaller cells and so packing more bits in one wafer reduces the cost per bit of memory. Memory cells that use fewer than 4 transistors are possible. However, such 3T, 17, 18, or 1T cells are DRAM, not SRAM. Even the so-called 1T SRAM. Access to the cell is enabled by the word line, WL in figure, which controls the two access transistors M5 and M6, which, in turn, control whether the cell should be connected to the byte lines, BL and BL. They are used to transfer data for both read and write operations. Although it is not strictly necessary to have 2-bit lines, both the signal and its inverse are typically provided in order to improve noise margins. During read accesses, the bit lines are actively driven high and low by the inverters in the SRAM cell. This improves SRAM bandwidth compared to DRAMs. In a DRAM, the bit line is connected to storage capacitors, and charge sharing causes the bit line to swing upwards or downwards. The symmetric structure of SRAMs also allows for differential signaling, which makes small voltage swings more easily detectable. Another difference with DRAM that contributes to making SRAM faster is that commercial chips accept all address bits at a time. By comparison, commodity DRAMs have the address multiplexed in 2 halves, i.e. higher bits followed by lower bits, over the same package pins in order to keep their size and cost down. The size of an SRAM with M address lines and N data lines is 2M words, or 2MN bits. The most common word size is 8 bits, meaning that a single byte can be read or written to each of 2M different words within the SRAM chip. Several common SRAM chips have 11 address lines. Thus a capacity of 211 equals 2048 equals 2K words, and an 8-bit word, so they are referred to as 2K8 SRAM. The dimensions of an SRAM cell on an IC is determined by the minimum feature size of the process used to make the IC. SRAM operation. An SRAM cell has 3 different states: standby, the circuit is idle, reading, the data has been requested, or writing, updating the contents. SRAM operating in read and write modes should have readability and write stability, respectively. The 3 different states work as follows: standby. If the word line is not asserted, the access transistors M5 and M6 disconnect the cell from the bit lines. The 2 cross-coupled inverters formed by M1 and M4 will continue to reinforce each other as long as they are connected to the supply. Reading. In theory, reading only requires asserting the word line WL and reading the SRAM cell state by a single access transistor and bit line, for example M6, BL. However, bit lines are relatively long and have large parasitic capacitance. To speed up reading, a more complex process is used in practice. The read cycle is started by pre-charging both bit lines BL and BL to high, logic 1, voltage. Then asserting the word line WL enables both the access transistors M5 and M6, which causes one bit line BL voltage to slightly drop. Then the bland BL lines will have a small voltage difference between them. A sense amplifier will sense which line has the higher voltage and thus determine whether there was 1 or 0 stored. The higher the sensitivity of the sense amplifier, the faster the read operation. As the MOS is more powerful, the pull down is easier. Therefore, bit lines are traditionally pre-charged to high voltage. Many researchers are also trying to pre-charge at a slightly low voltage to reduce the power consumption. 19, 20, writing. The write cycle begins by applying the value to be written to the bit lines. If we wish to write a 0, You would apply a 0 to the bit lines, i.e. setting BL to 1 and BL to 0. This is similar to applying a reset pulse to an SR latch, which causes the flip-flop to change state. A 1 is written by inverting the values of the byte lines. WL is then asserted and the value that is to be stored is latched in. This works because the bit line input drivers are designed to be much stronger than the relatively weak transistors in the cell itself, so they can't easily override the previous state of the cross-coupled inverters. In practice, access MOS transistors M5 and M6 have to be stronger than either bottom MOS, M1, M3, or top PMOS, M2, M4, transistors. This is easily obtained as PMOS transistors are much weaker than MOS when same-sized. Consequently, when one transistor pair, for example M3 and M4, is only slightly overridden by the right process, the opposite A transistors pair, M1 and M2, gate voltage is also changed. This means that the M1 and M2 transistors can be easier overridden, and so on. Thus, cross-coupled inverters magnify the writing process. Bus behavior. RAM with an access time of 70 ns will output valid data within 70 ns from the time that the address lines are valid. Some SRAM cells have a page mode, where words of a page, 256, 512, or 1024 words, can read sequentially with a significantly shorter access time, typically approximately 30 ns. The page is selected by setting the upper address lines, and then words are sequentially read by stepping through the lower address lines. Production challenges. With the introduction of the FIN-FET transistor implementation of SRAM cells, they started to suffer from increasing inefficiencies in cell sizes. Over the last 30 years, from 1987 to 2017, with a steadily decreasing transistor size, node size, the footprint shrinking of the SRAM cell topology itself slowed down, making it harder to pack the cells more densely. 4. Besides issues with size, a significant challenge of modern SRAM cells is a static current leakage. The current that flows from positive supply, VDD, through the cell and to the ground, increases exponentially when the cell's temperature rises. The cell power drain occurs in both active and idle states, thus wasting useful energy without any useful work done. Even though in the last 20 years the issue was partially addressed by the data retention voltage technique, DRV, with reduction rates ranging from 5 to 10, the decrease in node size caused reduction rates to fall to about 2.4. With these two issues, it became more challenging to develop energy-efficient and dense SRAM memories, prompting semiconductor industry to look for alternatives such as STT-RAM and FRAM. 4.21. Research. In 2019, a French institute reported on a research of an IAT-purpose 28 nm fabricated IC. 22. It was based on fully depleted silicon on insulator transistors, FDSOI, had two ported SRAM memory rail for synchronous forward/asynchronous accesses, and selective virtual ground, SVGND. The study claimed reaching an ultra-low SVGND current in a sleep and read modes by finely tuning its voltage. 22. See also. Flash memory. Miniature card, a discontinued SRAM memory card standard. In-memory processing.
Yes, stop. And I was too fallen asleep. Was last edit few days ago. But let's upload this. Next one is 21 pages, so I need a small break because I'm close to fall asleep because it's so hot in my living room. So next one is 21 pages. A lot I don't understand, and I'm Normally I'm very sleepy every day because I not sleep not enough in the night, and it's very hot in my living room always. Like now it's 30 degrees, so I'm getting sleepy like this one. When I'm reading I have problems to stay awake. So I'll take a small break and start upload this.